Welcome to lesson number 8. Today we're going to talk about words, equations, numbers, and graph. Again, in lessons 6 and 7, we explored the different forms of representations. The first, words, as in a problem where suppose you had this and this and you had to come up with an equation. Second, we had the equations, y equals ax plus b. Thirdly, we had the numbers, the XY tables of input-output values. And fourth, we had the graphs that gave us straight lines, either rising or falling or staying horizontal. I alluded to the general, usual, or common order of things in a typical algebra class, and that is usually we go from a story that someone else has written for us. We come up with an equation. We plot a few points, and then we join them with a graph. Well, today I'm going to try the opposite order. What we're going to try to do is go from graphs to equations, to numbers, and back to words. Remember what I told you when I said beware of one-way mathematics? We have to try to go back and forth. And the reason I'd like to ensure that you can, with ease, go back and forth between or among these different forms of representations, that would mean that really you've understood not just the processes, but also the concepts behind them. Today, we will tackle two types of activities, as you see in the next visual. The first I'd like to do is start with some numbers from an input-output table, go to the equation, see if we can find the ax plus b equation, and then invent a story or two that might go along with it. Secondly, I'd like to start with a linear graph. From the graph, derive the equation, and from the equation, again, invent a story that might go along with it. It's much more challenging to invent a story that is suitable to the equation and the numbers you've found yourself than getting an equation or a graph that's handed to you and thought out by someone else. So I'm going to again ask you to be very creative. And obviously, if you can synthesize the two types of activities we're going to do today, you'll be able to do the whole circle backwards from the usual way, and that is from the graph to the input-output values, which are numbers, to the equation, which is symbolic, and back to the story that you can make up. I think we're ready to begin activity 1. As I said, we'll start with an input-output table, then go to an equation, and then come up with an appropriate story. So let's go to our mathematics technology and get started, see what it has in store for us today. So here in my calculator, we have a table of input-output values, a very simple one. Let's look at the values. When x is 0, y is 0. When x is 1, y is 7. When x is 2, y is 14, and so on. 3, 21, 4, 28. Notice that I keep using x and y and input-output. I want to keep repeating that because when you use the graphing calculator, you have x's and y's up there, but we know that the x is the input and the y is the output. Okay, so this function goes on, and each time we find a value on the right column that corresponds to the value in the left column. Now, we said that our goal here was to go from the table of values to try to figure out an equation. Well, we saw in last class and the class before that up here, where x is 0, we always find the y-intercept, and that's the b value. So when x is 0, y is 0. What does that mean? That means that the function passes through the origin. b is 0. Now the only other element we need is to know what a is. Well, let's look what happens. When I go from 1 to 2, my increment is 1. When I go from 7 to 14, my increment is 7. Let's try again. When I go from 2 to 3, my increment is 1. When I go from 14 to 21, my increment is 7. What is that ratio? It's 7 to 1. But 7 to 1 is 7. So we've found our A value. Now we are ready to write down on our transparency what we've come up with, the A, the B, and write the equation. So let's do that. So we found that in the table of XY values, we had X0 for Y0. Well, we said that that meant that 0, 0 was our y-intercept. But we know that the y-intercept means that we've got the b value. Also, we saw in the table that whenever two consecutive points on the output column had a change of 7, the corresponding points in the input column had a change of 1. So our ratio, which was our slope, was 7 to 1, which is 7. But that's our A value. So we've got the B, we've got the A. We can now write the equation. Y equals AX plus B, where A is 7, B is 0. That gives us 7x plus 0, but we write 7x. There is my equation. Y equals 7x. So, what have we done? Let's recap very quickly. We started with a table of input-output values. It didn't come up on a graphic, it didn't come up on a chart, it came up in the computer because I had stored it overnight. We had some x values, we had some y values. Then we tried to find a relationship and we saw what the x-intercept was, what the y-intercept was, we saw what the slope is, and we came up with an equation. Y equals 7x. A very simple equation, and we know that since b is 0, it will go through the origin. We also know that a is positive, so it's a rising function. That should be a mental image by now. You see 7x, you know that the function rises, and it goes through 0. We have one more point to make to complete the cycle that we wanted to complete, and that is, let's try to come up with a story. The first possibility would be that 7 could be the rate of change. But what change? Time and distance. Well, you know, you maybe drive or you've been driven. We know that speed is a very typical rate of change. Miles per hour. But there's another way we can look at speed, and that's meters per second instead of miles per hour. Well, this could be the speed at which you run. You could run 7 meters per second. That's a possible rate at which you run. If you're an Olympic runner, you would run faster. If you're out of shape, you'd run slower. But that's possible. So why don't we go back to our calculator, our mathematics technology, and answer a question. For example, if that were your running rate, 7 meters per second, how long would you need at that rate to run a 100-meter dash? Let's go see. So here we have in L1 column the x values, 0, 1, 2, 3, 4, 5. That could be the seconds, the number of seconds you run. And in the L2 column are the output or y values, 7 meters, 14 meters, 21 meters, and so on. You can disregard column L3 right now. That pertains to another problem we're going to do a bit later. Remember that we've seen very often that we go from lists to the tables. The reason I stored the values in lists this time is so we can plot them like they do in statistics. So let's make sure we have our stat plot on. Let's pick on plot 1, turn it on, and now we can go to zoom. We've seen this many times now. We go to zoom stat and we plot. There are the points, and there is that line that goes through them. Now, once again, the discussion about the points versus the line. If we have just the points, those are the speeds and the distances, rather the times and the distances you cover at the unit seconds, 1 second, 2 second, 3 second, 4 second. But in between, you've got all the other times, and that is you might run 4.5 seconds or 6.25 seconds. So let's delete those points and just look at the continuous graph. So we have to go back to stat plot, turn them off, and go back to graphing just the continuous line. So remember, the question was, how long will it take you to run 100 meters? Let's use the trace button and review what that gives us. That tells us, as I move along the line, that at this number of seconds, I run this number of meters. So let's move until we find in the y value 100, and that'll give us an idea of how many seconds we take. So if I go up, I'm looking for 100. Here we go, we're getting close, 99.41 and 100.75. You see on this computer screen, we don't have all the possible points on that line, but this gives us an idea. At 99.45, our time is 14.2 seconds. If I move it to the next pixel at 100.75 meters, I'm at 14.39 seconds. Well, that's pretty close, except that very often when you're in a competition especially, we need a more specific, precise time. So let's see how we can do that. One thing we haven't visited too often is the zoom menu. Let's pick zoom in, which will really do just that. It will zoom in at that point to give us more precision. So I'm going to select 2 for zoom in, and now I push enter and I retrace that little piece of the line. I push trace again, and now I'm going to have more pixels and more precision in through here. So let's see. Look at that. I have 99.75, 100.0. That's already better than before. Tells me that I'm closer to 1429 now. Let's zoom just for fun one more time. Students love zooming in. So that was 2 for zoom in. We're going to zoom one more time, push the trace button, and see if we get even closer to the 100 value exactly. There's 100.16, 100.08. Look at that. We have 0.00, very close to 100. So this is probably as close as I can get on my computer, 14.28. Now, I'd like to go to our transparency and look at the algebraic manipulation that would give us the exact value in case we're still not satisfied with 100.00. We want exactly 100. What is the time x that I need at that rate to run exactly 100 meters? So let's do the little manipulation by hand. The symbolic equation we found was y equals 7x, where y was the distance. The distance was measured in meters, and x was the time, and the time was measured in seconds. That's your supposed speed or rate when you run. Well, what was the question? The question was, what will my time be, or your time, for your distance to be 100 meters? So y is given, but x is unknown. Well, we're a little ahead of ourselves here, and we're solving an equation, even though we're not at that lesson yet. But that's all right, it's a very simple one. So if we replace 100 into y and x into x as it is, we get 100 equals 7x. Now we saw that x was very close to 14.29 on the calculator. But what we're doing here is trying to see how could we do it by hand and find the exact value. Well, there's just one little manipulation to do, and that is if I divide the left side and the right side by 7, you know that. 7 divided by 7 gives me 1, but 1x is just x. And 100 divided by 7, if you were to take your graphing calculator or do it by hand, you would find 14.28 8, 5, 7, and as far as you want to go, and as much precision as you need. I know you can do that both by hand and with the calculator, so there's no sense in showing that division right here. Well, you can imagine all sorts of other different stories that would go along with the simple equation y equals 7x. We just came up with one here. Little original. It involves you. It's your speed when you run. But another example would be 7x could be, x could be the number of boxes of chocolates you want to buy, and 7 could be the price per box of chocolate. So if you want to get 3 boxes, it would be $21. And then you could ask the question, if I have $100 and I want to buy as many boxes as I can because they're on sale and I want to get some Christmas gifts early, then you would look for the same type of question. 100 equals 7x. Mathematically, it's the same equation. The story would differ. Well, now we're ready to do another activity of a different type. Let's start with a table again, and let's look into the graphing calculator, our mathematics technology, and see what numbers I've stored in for you this time. Here is our table of input-output values again, the numerical table. And now we have, again, in the x column, 0, 1, 2, 3, 4, 5, 6, another friendly table. The whole numbers are there. Sometimes it's more complicated because you have numbers in between, but these are our first trials and experiences, so we're keeping it simple. In the y column, or output column, we have 3, 4.5, 6, 7.5, and so on. Each of these y values, or output values, correspond to the x, or input values. So what can we observe from this table? Well, again, there are two things we can see. The b value, and that always lives right here. When x is 0, y is b. That is the y-intercept. When x is 0, I'm on the y-axis, and that's the only time I'm on the y-axis, when x is 0. So 0, 3 is 0b, or b is 3. Now what about a? Well, a has to do with the change from one y value to the other. What is the change from 3 to 4.5? Well, we should be good enough at mental math to see that that's 1.5. What's the corresponding change in x? It's 0 to 1, which is 1. Let's try again. 4.5 to 6 is 1.5. The change on the x column is 1 to 2. So each time we have a change of 1.5 on the right column and a change of 1 in the left column. Well, that tells us that the ratio of 1.5 to 1 is 1.5. So A is 1.5. Well, I think we're ready to go back to our transparency and write down the equation that we've just found. To recap. So we found that in our XY table, we had a 0 for x and a 3 for y. Well, that tells us that our b equals 3. We know that by now. The other thing we saw was that for any two consecutive values in the y table, we had a change of 1.5. In the x column, the change was 1. That gives us a slope, or a rate of change, of 1.5 to 1. But that's 1.5. Now, again, if you don't take two consecutive values, but suppose we took two that were further away, for example, the point that was, we had a 0.26, if you recall, and we had a point, another one would be, let's say, 6 and 12. How's that? Let's take those two. Well, the change in x is 4. The change in y is 6. So we have a slope of 6 to 4, but that's 3 to 2, and that's 1.5. So again, our A is 1.5 no matter what 2 points we take, two that are close together or two that are far apart. So now the equation that we're ready to write is 1.5x plus 3. There is our nice linear function where this is my A and this is my B. You see, we found that from the table. Now, what could this equation possibly represent? Well, again, let's think. The difference is that last equation had a B of 0. Here we have a B of 3. So something I know you're very creative too, and you're thinking of all sorts of stories that could go along with this, but the more we do, the better you'll get at it. Imagine you're in Europe or in Africa, you're somewhere far away, and you want to call home, and you have a calling card. Well, calling cards are expensive when we do long-distance calls. 3 could be the amount of money, the dollars, that it would cost to just use the card. That means before you even make a call, before you even use 1 second or 1 minute, you would pay $3. And then X would be the number of minutes that your call would last. So if it's 1 minute, the price, Y, would be $1.5 plus the $3 charge to use the card. The 1.5 would be the minute rate, the cost per minute. So if you make a 2-minute call, it would be 1.5 times 2 minutes plus that $3 charge. So that $3 charge is your constant, even if you don't make a second of a call. So let's ask the following 2 questions. Suppose I make a 10-minute call. How much would it cost me using that credit card, or that calling card rather? And another question would be the other way around. Suppose I get a bill of $15. How long did I speak? So let's go back and do that computation. Here we have the input values in my list 3 and the output values in my list 4. I'm back to the list instead of the tables again. You know why, because I want to plot it. So let's go to the plot for L2, L3 and L4. That's where my values are, and let's plot it. Let's make sure it's on. It was not on, it's off, so here we go. And now we go to Zoom. We go down to Zoom Stat for statistics, and there are our points, and there is the line. So here we go. We have along this axis the number of minutes we're going to speak, and on this axis the number of dollars we're going to spend with that calling card. Again, since we are also interested in all the values in between, because we could make a 3.5-minute call or a 5.2-minute call, or we could have a few seconds in between. Let's delete those points and get a continuous line. So we want to put stat plot off, and that's number 4. Turn off our plots and go back to the graph, and there's our continuous line. So the question was, let's trace it. For a 10-minute call, when X is 10, how much money will I pay? Well, obviously, I've got to go a little further to find X equals 10. And there we are, approximately, all right? 10.04 minutes would be about $18. We can do what we did last time and zoom in. Here's my zoom menu. I pick 2 for zoom in, and I trace again. I've really focused much closer here, and now I'm seeing if I can get closer to $18. I can get to 18.06. Well, again, that's close enough. So that's about $18 for a 10-minute call. If the question were the other way around, say I get a $25 bill or a $20 bill, whatever amount of money you want. I look for the Y equal to 20. It's coming. Y equals 20 is on its way. There it is, about 20. If it's $20, then I know I've spoken for a little over 11 minutes. Well, that completes our first type of activity, where we start with a table, we derive the A and B value, we come up with the equation, and then the last task is to find a story. And we did pretty well. We came up with 2 interesting stories. Now it's time for our second type of activity, starting with a graph, then deriving the numbers, then finding the equation, and then coming up with a story, which I might let you figure out too. Each time, try to figure out before I say it. All right, here we go. Here is a graph. We see that it's a falling graph. The function is decreasing. And if we look at what we did yesterday, or the lesson before that, we have here, from here to here, a change of X that is from 20 to 40, and a change of Y that's from 500 to 400. Let's do it again. From here to here, our horizontal change is 40 to 60, that's 20, and our y change is 400 to 300. We can read that there. So that's a negative 100. Let's do it again. The change in x is 60 to 80. Well, that's a 20 move. And the change in y is 300 to 200. And that's a negative, right here, a negative 100. So let's make a table and summarize the values we have. We have an x and a y table where a few values are given. 20, we have 500. 40, we have 400. 50, no, that was right. 20, 40, 60 is 300. And 80 was 200. Well, we saw that the change in y is negative 100. The change in x is always 20. Here we have a change of negative 100 and a change of 20. One more time, negative 100 and 20. So our a value, the slope, is negative 100 to 20. But if we simplify that, we have negative 10 over 2, that's a negative 5. What about our b value? Well, if we go back up here, this is 20. If I go backwards, I would have a 0 here to have a change of 20. And if I have another negative 100, I would start at 600. So I found once again my b value. b is 600. Well, with these two values, we have what we need for the equation. Y equals negative 5x plus 600. Well, what could that represent? It could be different things. One thought that came to my mind was a demand curve. What does that mean? Well, suppose you had a really interesting video that's out, the latest, hottest video, and it was X dollars. Well, when it's at $20, the store is selling 500 of them. If you raise the price to $40, they're only going to sell about 400. If you raise it to $60, they'll only sell about 300. And that's a very interesting graph when we talk about economics and how should sellers price their objects or their commodities. Very often there's that maximum equilibrium point where you have just enough money and you sell just enough. But when it gets too expensive, the demand for it falls. And when it's very expensive, nobody wants it anymore. So that's just one thought. You try to figure out an explanation for that equation. One last one, and I'll let you figure this one out. Very easy. A horizontal function. Very simple. When x is 0, y is 20. When x is 1, y is 20. When x is 2, y is 20. Everything is 20. That looks very simple, but it can often happen. No matter what x is, from negative 3, negative 2, negative 1, 0, 1, 2, 3, and so on, y is always 20, 20, 20, 20. That is boring. But what is that type of function? It's just a horizontal line, the b is 20, and the a is 0, because my change in y is 0. Isn't it? So the equation is y equals 0x plus 20. But that's y equals 20. Well, that's the last example for today. And that's a very simple function, but sometimes the simplest things are the things we forget. Y equals a constant. That means that b is 20, a is 0. That's a horizontal line. That's a function that doesn't change. Can you think of a meaning for y equals 20? I can. Y could be the temperature. And 1, 2, 3, 4 are the hours in a day. Well, you can imagine in a summer day that your temperature could be 20 degrees Celsius for about 8 hours. The function wouldn't go up, the function wouldn't go down, it would stay constant. The temperature is constant. So you have a constant function. Well, I hope that this exploration has helped you today. Words, functions, equations, graphs, and tables, that you can put all together and make more sense about it.